Imagine vast clouds in space. These are not Earth clouds, they are cosmic nurseries. We call them nebulae. Nebulae are huge, they stretch for light years. Inside there is gas and dust, mostly hydrogen and helium. Tiny grains of cosmic dust float around. These are the raw materials for stars. These nebulae are incredibly cold, and they are very, very diffuse. The particles are far apart. But there are so many particles, enough to build billions of stars. Think of them as giant stellar factories, quietly waiting for something to happen. A trigger is often needed, perhaps a shockwave from a nearby exploding star, or the gravitational nudge from a passing galaxy. Once disturbed, gravity starts its work. Small regions within the nebula begin to clump. More and more material gets pulled in. These clumps are called molecular clouds. Inside the denser parts of the nebula, gravity continues its relentless pull. Material falls inward, toward a common center. The clump of gas and dust starts to spin. This is due to the conservation of angular momentum. Think of an ice skater pulling in their arms. They spin faster and faster. The same thing happens with this cosmic clump. It spins faster as it gets smaller, forming a flattened disk around a central core. This central core is called a protostar. It's not quite a star yet, but it's getting warmer as more material falls onto it. The pressure at its center increases. This pressure generates heat. The protostar begins to glow faintly, mostly in infrared light, hidden deep within its dusty cocoon. We need special telescopes to see them. The protostar stage can last for thousands of years. It's a crucial phase of development. The protostar is still gathering mass. The core of the protostar keeps getting hotter and denser under gravity's immense pressure. This relentless force causes the atoms within to collide more frequently and with greater intensity. Temperatures soar to millions of degrees Celsius, creating an environment so extreme that it defies imagination, around 10 to 15 million degrees. This is the threshold where the magic begins. This is the magic number, the point at which the conditions are just right for a remarkable transformation. At this point, something amazing happens. The core becomes a cauldron of nuclear reactions. Nuclear fusion begins in the core. Hydrogen atoms start to fuse together, forming helium. This is the birth of a true star, a celestial body that will shine for eons, the moment it truly starts to shine. A new beacon in the cosmos. A cosmic light switch is flipped. The star's light pierces the darkness. What is nuclear fusion? It's a powerful process, one that fuels the universe. Hydrogen atoms, the star's main fuel, are squeezed together with such force that they combine to form helium atoms. This fusion releases an immense amount of energy. This process releases a tremendous amount of energy that radiates outwards, energy in the form of light and heat, the very essence of a star's brilliance. This is the same process that powers our sun, the heart of our solar system. It's Einstein's famous E = mc2 in action. Mass is converted into energy. Mass is converted into energy, a transformation that fuels the star's radiance. This outward push of energy from fusion finally balances gravity's inward pull. The star becomes stable, it stops contracting, it reaches a state of equilibrium. This state is called hydrostatic equilibrium, a delicate balance that allows the star to shine steadily, a delicate cosmic balancing act. The star maintains this equilibrium for a significant portion of its life. The star will maintain this balance for a long time, for millions, even billions of years. For most of its life, in fact. This is the star's main sequence phase. The star has now entered its main sequence phase, a period of stability and sustained energy output. It will shine steadily for billions of years, a beacon of light in the vastness of space. Once fusion ignites, the star settles down into a stable state, marking the beginning of its main sequence phase. It enters the longest phase of its existence, a period that can last billions of years. This phase is known as the main sequence, where the star spends the majority of its life. Our Sun is a prime example of a main sequence star. It has been in this phase for about 4.6 billion years, steadily burning its hydrogen fuel. And it will remain in this stable state for billions more, providing light and warmth to our solar system. During this phase, the star is stable, maintaining a delicate balance between gravity and pressure. It steadily fuses hydrogen into helium in its core, a process that releases immense energy. This fusion process is its primary job, its life's work, converting mass into energy. Day in, day out, the star continues this cycle, shining brightly in the cosmos. The lifetime of a main sequence star depends critically on its mass, with larger stars burning through their fuel more quickly. Massive stars are like cosmic gas guzzlers, consuming their hydrogen at a rapid pace. They are much hotter and brighter, shining with a blue tint. These stars burn through their hydrogen fuel very quickly, much like a firework display. As a result, their main sequence lives are short, often lasting only a few million years. Perhaps only a few million years, a blink of an eye in cosmic terms. Think of a rock star, live fast, die young. These stars burn bright and fade quickly. These are the blue giants of the cosmos, shining with incredible intensity and brilliance. Smaller stars, like our sun, are much more fuel efficient, burning their hydrogen slowly. They burn their hydrogen slowly and steadily, much like a slow-burning candle. Their main sequence lives are much longer, stretching into billions or even trillions of years. Billions or even trillions of years for the smallest and most efficient stars. For the smallest red dwarf stars, their longevity is unmatched. These stars are cooler and dimmer but incredibly long-lived. They are the marathon runners of the universe, enduring for eons. They will outlive almost everything else, quietly shining for eons, long after other stars have faded away. Section 5. Running low. The red giant phase begins. All good things must come to an end, even for a star on the main sequence. After spending billions of years fusing hydrogen into helium, the star's core begins to change. Eventually, the hydrogen fuel in its core starts to run out. The once abundant hydrogen is now mostly depleted. The star has been fusing hydrogen for billions of years, creating a stable balance between gravity pulling in and pressure pushing out. Now, the core is mostly helium ash from all that hydrogen burning. This helium core is inert, unable to sustain fusion at this stage. Fusion in the core begins to slow down and then it stops. The star's energy production drops significantly. This is a critical turning point. The balance that kept the star stable is now disrupted. Without the outward pressure from fusion, gravity starts to win the battle. The core begins to collapse under its own weight. The helium core begins to contract. This contraction is a natural consequence of the loss of fusion pressure. It gets squeezed by its own weight, becoming denser and hotter. This contraction heats up the core, and it also heats a shell of hydrogen surrounding the core. This shell is just outside the core. The increased temperature in this shell ignites a new phase of fusion. The hydrogen in this shell gets hot enough to start fusing into helium. This process is known as hydrogen shell burning. This is called hydrogen shell burning. The energy released from this shell burning is immense. This new burst of energy from shell burning is actually more intense than before. It reignites the star's outer layers. It pushes the star's outer layers outward. The star begins to swell. The star begins to expand dramatically. It grows to many times its original size. It swells up to enormous sizes, becoming hundreds of times larger. This transformation marks the beginning of the red giant phase. Its surface cools down as it expands, so it shines with a reddish color. This is why it is called a red giant. Section 6. Two paths diverge. A star's mass seals its fate. What happens next depends entirely on the star's mass. Mass is the ultimate decider of a star's destiny. There are two main paths, one for low-mass stars, like our sun, and another for high-mass stars. Stars much more massive than our sun. The dividing line is roughly 8 times the mass of our sun. This is a crucial branching point. In the life story of every star, low-mass stars have a relatively gentle end, after the red giant phase. Their cores are not massive enough to reach the temperatures needed to fuse heavier elements beyond helium, or at least not much beyond it. Some helium fusion can occur in the core, creating carbon and oxygen, but that's usually as far as it goes. They don't have the gravitational oomph for more. High-mass stars, however, live life in the fast lane, and they go out with a spectacular bang. Their cores are much hotter and denser after they exhaust their hydrogen. Section 7. A star's quiet end, white dwarfs and cosmic ghosts. Let's first follow the path of a low-mass star, like our sun, after its red giant phase, and after it fuses helium into carbon and oxygen, the star's outer layers become unstable. They begin to drift away into space, pushed outwards by stellar pulsations, and the radiation from the hot core. This creates a beautiful, glowing structure, called a planetary nebula. Despite its name, a planetary nebula has nothing to do with planets. Early astronomers thought they looked like planets through their small telescopes. These nebulae are shells of ionized gas, illuminated by the central star's remnant. They come in many stunning shapes, rings, bubbles, or butterfly patterns. A final, fleeting display of cosmic art, before the star fades away. What's left behind at the center? The hot, dense core of the former star. This is called a white dwarf. It's incredibly compact. Section 8. Going out with a bang, the supernova spectacle. Now let's turn to high-mass stars. Their end is far more dramatic. Remember, their cores build up iron, and iron fusion doesn't release energy, so the core can no longer support itself against the crushing force of gravity. In a fraction of a second, the iron core collapses catastrophically. It shrinks from the size of Earth to a ball just a few kilometers across. This rapid collapse causes a rebound. A powerful shockwave blasts outwards, through the star's outer layers. This is a supernova explosion, one of the most energetic events in the universe. For a brief period, the supernova can outshine an entire galaxy, releasing more energy in moments than our sun will in its entire lifetime. It's a truly awesome spectacle. The explosion hurls the star's outer layers into space at incredible speeds. These expanding shells of gas and dust are enriched with heavy elements. Section 9. Into the darkness, black holes and the universe reborn. For the most massive stars, even a neutron star is not the final stage. If the collapsing core after a supernova is more than about 3 times the sun's mass, nothing can stop its complete collapse, not even neutron degeneracy pressure. Gravity wins the ultimate victory. The core collapses indefinitely, crushing itself down to an infinitely small point, a point called a singularity. This creates a black hole, an object with gravity so strong that nothing, not even light, can escape. Once it crosses a boundary, called the event horizon. The event horizon is the point of no return. Black holes are truly mysterious objects. They warp space-time around them. They are invisible, detected only by their effects. Their gravitational pull on nearby stars and gas. Black holes come in different sizes. Stellar black holes are formed from massive stars. Supermassive black holes millions or billions of times the sun's mass reside at the centers of galaxies.